Welcome to Math 1314, Section 5.4. In this section, we look at something called nonlinear systems. In the previous section, we looked at linear systems. So why is this nonlinear? Well, it's because one of the equations has a squared in it. But we're still looking at the same question, and that is, given these two objects, if we graph them, do they intersect? And if they intersect, where? Well, the first one you should recognize is x squared, our parabola, minus 3. So it's a parabola shifted down by 3. And in the second equation, if I solve for y, move the y to the right, move the 3 to the left, then I see it's a line going upward, crossing at minus 3. And so if I make a rough sketch of that situation, here's our parabola, here's our line, and they do seem to be intersecting at 2 points. Now, it's just a rough sketch, so don't take anything too strongly from where. Now, they both do intersect at 0, minus 3. That's true because the parabola is shifted down by 3 and my line is crossing at minus 3. All right, so, how do we solve it? And we want us to solve it by substitution. All right, well, the easiest way is both of these things are y. Y is y. Well, one of the y's is x squared minus 3. The other y is 2x minus 3. Well, let's get everything on one side. So if I move this minus 3 to the left, it would cancel this one. And now move the 2x to the left, and I notice I get something that's factorable. I take out the common x, and I get x times x minus 2. And so now if I set each one of these to 0, I get x is 0 and x is 2. Now we're not done because I need to figure out the y that goes with each one of those x's. Alright, well, let's see how to do that. So if I use x equals 0, y is 0 squared minus 3, and so y is minus 3. Therefore, that one point was at 0, minus 3. If I let x be 2, 2 squared is 4, 4 minus 3 is 1. And so the other point is at 2, 1. Not too bad. All right, question 2. Let's see, we have a different non-linear system. Let's see, one of these, y is minus 3x. That's a downward line through the origin. This cube root, if you think way back to our basic shapes, it was one of our basic shapes. And here it is. It's the cube root function. So the cube root function looks like this. Ours has a minus, so it's actually flipped over. So let's take a look at that. Let's see. So here's my line that's going down through the origin. Here's my flipped over cube root of x. And it does seem to have 3 points of intersection. Now, one of them's easy to see. One of them is the origin as one place, but not sure where the others are occurring. All right, well, let's take a look more. All right, so they say graph minus 3x, so I did that. So that's sitting there on this. And so I'm looking, and visually you can see where they're at. Let's see, so if I actually solve it, y is y again, Minus 3x is minus 3 cube root of x. So first off, get rid of the minus 3's. We get this to solve. Now one of the ways to get rid of a cube root is to cube both sides. If I did that, I get x cubed is x. Move this x to the left. And so now you could factor this common x out. X squared minus 1 is x plus 1, x minus 1. And so I get three answers for x, 0, minus 1, and 1, which makes sense because we were seeing three places of intersection. Well, how do we figure out the y? Well, take each of the x's, plug it in, and calculate the corresponding y. And so we get the point 0, 0. That didn't look very good. We get the point 0, 0. We get the point 1 minus 3. And we get the point minus 1 positive 3 for the three places of intersection. All right. Question 3 says solve by any method possible. In this case, the addition method. All right, so let's see. Can I add them up and have something cancel? Well, I'm looking at the y's, and I think I can multiply this by 4 all the way across. So multiply it by 4, add them up, I get 27x squared. The y's cancel, and I get 27. And if you divide both sides by 27, you get x is plus or minus square root of 1, which is plus or minus 1. All right, well, what are the y's that go with all that? Well, let's see. If you plug in 1, I get y squared is 9. So y is plus or minus the square root of 9, or plus or minus 3. So for this 1x, we actually get 2 points. Similarly, if we plug in minus 1, we get the same situation where y is plus or minus 3. And so for that x, we get another 2 points. So in total, there's actually 4 places those two graphs intersect. And for the last case, we get this particular nonlinear system. I don't have any lines, so let's see what's going on here. Well, if you remember, what does the square root function look like? It looks like this. 1 over x was one of our other basic shapes, looks like the following. Remember, the square root doesn't have a left side. It starts here at the origin. So from my rough graph, I'm noticing there should be one place where the two intersect. All right, well, how can we go about solving this? All right, so again, I try the technique of y equals y. So now what am I going to do with this? This looks terrible. Well, I'm going to try to square both sides, because if I square a square root, it goes away. All right, I get this. And so I get a big number equals x cubed. Now formally, I would take this and I would have x cubed minus 4096 equals 0. It turns out that this particular problem has 3 solutions. Now, 2 of them are complex numbers and I don't have to worry about them. That's why I made this rough sketch to give me kind of an idea how many places was I looking for. Well, in this case, I know there's only one. Therefore, I solve this by taking the cube root of both sides. I get x is 16, and then I simply plug that in to figure out the y. Square root of 16 is 4, and so that one point of intersection is at 16, 4. Nonlinear systems can be rather difficult to solve, but these are relatively simple.